Hey everybody, this is the solution video, or the solution videos for the BCPC 2018 set. Last year I did a separate video for each of the problems, but there were just a bunch of videos. So instead of doing that and having people scroll through all of them, we're just going to do everything in one video, and then I'm going to put links to each problems in the description so that you can just jump to whichever thing you're interested in if you know how to do the easy ones. And because people are very impatient, we're going to jump right in and start with problem number 1, which is everybody do the flop. So in this problem, you're given several lines of input, and you have to keep reading input until you see everybody do the flop. So it's pretty straightforward, so let's get into it. So let's make this bigger. How do you do that? All right. Okay. I think I figured it out. Okay, so we made text bigger. Let's start with the scanner. And we want to import scanner, of course, and then we want to say that while s.next line, we can't use next because there could be spaces. So while that is not equal to what we're looking for, then we want to print wait for it, and then once we get the string that we're looking for, we want to print just flop. Okay. So hopefully you're able to get that in contest. Oh, we're missing a thing. Okay. So let's run it, see if it works. Wait for it, flop. And then this test case makes sure you don't do like start with or anything else that's crazy. Wait for it, flop. Alright, so that looks right. So there is everybody do the flop. So on to the next problem, funny pairs. So funny pairs is interesting. You're given a number x, and you have to output if there's some y that makes the pair xy funny. A pair of numbers xy is funny if x times x equals y plus y. So if x squared equals 2y, then it's funny. So if x times x equals y plus y, that means that x times x over 2 equals y. So if we know what this is, we can figure out what y is, but we also know that y has to be an integer. So if this isn't even, then y doesn't exist. And actually, we can just check if x is even, because if x is even, then x squared is even, and if x is odd, x squared is also odd. So we can make a new scanner. And I believe this problem is multi-test case. Oh. I'm trying to use a more quiet keyboard since last time the keyboard noise was a little bit annoying. So we're given x, and then we want to check if x is even. And x is small enough that we don't have to worry about long, since x only goes up to 10 to the 4th, and integers go up to 10 to the 9th. We're fine here. Hope you enjoyed the math pun with cosecant, which is, of course, 1 over sine of x. And then we can test this. 8. Can you do it? Cosecant, and then 0. Okay, so there you go. That's how to do funny pairs. If you haven't read the flavor text, I really recommend doing that because it is one of my favorite problems in the set, perhaps that I've ever written, even. So I think it's an interesting problem for how easy it is, at least. Okay, so the next problem is Goat Simulator, and in this problem you're given a bunch of obstacles. You're given n obstacles, and you're given a bunch of queries. And for each query, you have to count the number of obstacles between it, and you have to add up the total number of obstacles across all the queries. So there are a bunch of ways of doing this. Really, anything other than just the brute force iterate through all obstacles for every query will work. That won't work because it's 10 to the 6th squared, which would be 10 to the 12th, or 10 to the 6th times 10 to the 6th. That's just too slow. So there are a bunch of things you can do. One of the ones that I think is coolest is using a data structure called a Fenwick tree, or a binary index tree. And I'll link to an Algorithms Live video in the description. But Fenwick trees are really cool. They can do exactly what this problem's asking. And if you have the code for it in your hack pack or like in your notes or whatever, it makes this super easy. But also we can do other things, like we can sort the queries and the obstacles by index, and then we can iterate through them and keep a count of how many queries we're currently in right now. And then when a query ends, we subtract 1 from that. When one begins, we add 1 to that. And then when we're in an obstacle, we add 1 for each query, obviously. So we just add the number of queries. The other thing to note is that this could be greater than 10 to the 9th, because each query could cross every obstacle. So each of your 10 to the 6th queries could cross 10 to the 6th obstacles. So you got to use longs here. You got to be careful for that. And the last thing we can do, which I personally think is just easiest to implement, is to use prefix sums. So prefix sums are pretty cool. What they do is they count the number of obstacles before a given point, or the number of things from 0 up to the current index. And by doing that, we can easily check the number in a range. So that's what we're going to implement really quickly, and I'll show you how to do that. So this is goat. So we're going to need a scanner. And then first we're given the number of obstacles. So we're going to store how many obstacles are at each position. That way we can make our prefix sums really easily. So we're going to, at the position of each obstacle, we're going to mark that as there's one more obstacle there. Now we're going to make our prefix sums array. So obviously the number of things before or equal to position 0 is just the number of things at position 0. So presums at 0 equals delta at 0. And then up to presums.length, presums at I equals the number of things up to including there before plus delta at I. So the number of things up to and including position I is the number of things before position I plus the number of things at position I. And then we have to worry about the queries, so we're going to need a total, and we're going to need the number of queries, so we're going to iterate through each query. I don't know what Eclipse is doing here. Okay, and then we're going to want the start and the end. Okay, and then we have to get the number of things between start and end. And the problem guarantees that there's nothing at start or end, so we don't really have to worry about that, which is nice. But to do that, because of the fact that we don't have to worry about that, we can just do total plus equals presums at end minus presums at start. Then we can just print out the total. So that's the intended solution. Hopefully this makes sense. I can draw a quick little picture really quickly. So if we have 0, 1, 2, 3, 4, 5, 6, 7, and we want to find all the things from here to maybe here. What this thing right here is doing is it's finding all of the things up to here and then subtracting out this part. And then what you're left with is this part right here, which is what we're looking for. And then we would have to be careful about this right here, because like we're including this end and not including this end, which usually isn't good practice. But it's fine in this problem because we're guaranteed there won't be any obstacles on 5 or 1 in this case. So that's what that's doing, and that is GOAT. So moving on to the next number, it's Codeforce's handle. So Codeforce's handle is pretty cool. It's a counting problem of the set, so you gotta count kind of efficiently. It was similar to the problem about negligent Norbert from last year's set, so kind of mid-level counting problem. What this is asking you to do is, so you're given a Codeforce's handle. Oh, I should show you this, by the way. So the problem is made on, it's written about Peter. We go to codeforces.com, which is a famous competitive programming website. The #1 user right now is Peter. It's been Tourist for ages, but he lost a bunch of points recently. So now it's Peter. So this is who it's named after. He's a super good programmer from Russia, perhaps the best in the world. Tourist might also be the best in the world, depends who you ask. But it's about Peter. So he's got his Codeforce's handle, and Peter is taken. So he needs some new handle to take. So he removes some vowels from his name until he gets a name he's happy with. The question is, for some given name, how many possible sets of names are there? How many names could it map to? So one very important part of the problem is this line right here. Your program is only going to be run on names that don't have 2 adjacent vowels that are different. So Joan, for example, won't work. Also, importantly, you're not going to get something like that, because this is really tricky since the first letter and the second letter are different. But if you remove the first two letters, you get that. And if you remove the last two letters, you get that, and those are the same. So accounting for that gets really difficult without actually keeping track of them. You gotta figure out how these mappings are going to interact with each other, when it isn't really obvious how that's going to happen. Especially if you get complicated things like this. It's just like counting that is just a very difficult thing to do. But thankfully, we don't have to worry about that. We're just going to have continuous sections of one vowel and then some number of consonants, and then continuous sections of another vowel, and then continuous sections of another vowel, and then they're going to be all consonant separated. So it doesn't matter how many E's we pick here, for example. That's completely independent from the number of A's we pick and the number of A's we pick here, which is nice. So in order to count this, if we have these 3 A's here, the possible choices we have are we can have 0 A's, we can have 1 A, we have 2 A's, or we can have all 3 A's. So we have those 4 choices. If we only had 1 A here, then we can either have 0 A's or we can have the 1 A. And if we have 4 E's, we can have 0, 1, 2, 3, or 4 E's. So if we have n letters together, that leaves n plus 1 options. So the number of ways to do this is equal to this 4, so 3 plus 1, times this 1 here, plus 1, times the 4 plus 1. So 4 times 2 times 5 is 40. So there are 40 different possibilities for this. And then you can see that matches this sample. So Peter has just 2 times 2, John is just the 2, Steve is this 3 times this 2, and Elizabeth is 2 to the 4th because it's got 4 vowels that are all separate. So let's implement that. So we're going to need a scanner. And the first thing we're given is the end. Also, Y isn't counted as a vowel in this problem, which is important, I guess. So those are vowels. So we're going to get our word. Let's get it as a character array, actually. Okay, and now we want to iterate through all of the things in our word and keep track of the runs of vowels. So we don't really have to do this efficiently, even since the word is so small. It can only be like 100 characters long or something, 50 characters? No, 100 characters long. But still, that's like, we can do whatever we want basically to count this. So I'm going to make a variable that is the current length. And we don't have to worry about it being the same vowel as the one before, because that's guaranteed in the problem. So we can iterate through so if vowels that contains if it contains C as a string, then we're going to do one thing, otherwise we're going to do something else. And we're also going to want to keep track of the total number of ways. That is never going to overflow long. You can prove it. Like, worst case is a little bit more than 2 to the n over 2, which is about 2 to the 25. So it might even fit an int, actually. No, 2 to the 50. So it won't fit an int, but it will definitely fit in a long. So it's a little bit more than 2 to the 50, but not by much. So what we can do now is, if it contains a C, then we want to add 1 to our run length. And if it doesn't contain a C, then we want to account for our current run length, right? So total, we want to multiply it by run length plus 1. Then we want to say, okay, well, our run just ended. And we want to do that for each of the characters in the word. And once the word's over, if it ended in like some vowel, for example, we have to account for that still. So we could still be in a run. And if that's the case, we want to multiply the total by the run length plus 1, of course, because we could have an empty, or we could use none of those vowels. And then once we've calculated the total, we just want to print out what the total is for each case. Okay, let's see if this works. Four, 2, 6, 16. So it passes samples, so it doesn't necessarily work, but it there aren't any completely obvious errors in it. Okay, so that's handle. Hopefully my explanation kind of made sense, and drawing up the picture did a little bit too. And hopefully you understood how to do it. So now we're going to move on to tax evasion. So tax evasion is another really cool problem. I really like this one because of its implications in the real world. The inspiration for it kind of came from RJ's, which is an ice cream store in Elm Grove, Wisconsin, and they sell, or they used to sell, at least they stopped selling them, but they used to sell warheads, which are these little sour, like, pieces of candy that you can get, and they'd sell them individually for 5 cents. And because tax is 5% there, if you buy exactly 1 warhead for 5 cents, then the tax rounds down, so you don't have to pay any sales tax. So at the end of the school year, me and my friends would, when we were in like 6th, 7th, 8th grade, we'd bike to RJ's, and we'd buy warheads. And instead of buying like a bunch of them for $1, we'd buy them each individually for 5 cents each, because you can save a very significant amount of money, because if you bought 2 of them, you'd have to pay a whole penny in sales tax. So there'd be a pretty big difference. So that's kind of where that comes from. Here we made it easier because the sales tax of 5% has a ton of really weird cases that you have to handle. Here there are only 3 cases because it's divisible by 3. So the sales tax is 4/3. And to solve this problem, there are a couple things you got to notice. So if you have some price that's divisible by 3, then you're going to have to pay that tax exactly. And if some price is some multiple of 3, like let's say it's 4 cents, well, the first 3 cents we're going to have to pay 1 penny on in tax. And then that 4th cent, we might have to pay some tax on it, we might not, depending on the other things in our checkout cart, kind of. So the thing to notice about this problem is the only way to save money is to abuse the rounding on the taxation, right? Because you're going to have to pay 30% of your sales tax on it no matter how you buy it, but you might be able to kind of game the rounding system in order to round down as many times as possible. And you can even show that a greedy strategy works. So when I say greedy, I mean like you make the best decision now possible, and you just kind of live with that later. And it turns out that making the best decision now is also making the best decision in the long run. And that's not always true, but it is for this problem, because if, for example, you have some multiple of 3, well, then it doesn't really matter whether you check out now or you check out later. If you have some multiple of 3 plus 1, so like 4, for example, the first part of that 4 you're going to have to pay sales tax on no matter what, but then you have that extra 1/3, and that extra 1/3 will round down. So for buying something that costs 4, you'll only have to pay 1 cent in sales tax instead of like 1 1/3 cent of sales tax. So you can round down like that, and you can round down for 4, you can round down for 7, which is 1 more than 6, you can round down for 10. So any of those, for example, if we look at this, in this first sample, you can round down by this 10 by buying it alone. So here, they kind of trick you to say you can buy it with the 9, but you can also buy the 10 by itself, the 9, it doesn't really matter where you buy it, and then the 2 5s, if you bought 1 5 by itself, you would have to pay 1 extra penny in sales tax for the 2 part of the 5. So the first 3 you have to pay your 1 penny for, but the next 2 you also have to pay a penny for. So to avoid that, if we buy both of the 5s together, Well, since adding two multiples of 3 plus 2 together, that's the same as 1 multiple of 3 plus 1. Plus, like, since we just overlapped the two 2's, we've got that 3, right? So if I draw a picture here, you've got the 2 for this one, and then you have the 2 for this one. And then you might have other multiples of 3, but those don't matter. That's the same as you've got to pay 1 penny in sales tax for this, but then you don't have to pay for this. So this one is actually free, which is nice. So you get this one for free by buying 2 5s together. If you only have 1 5 or one thing that's 2 left over, then you're just going to have to suck it up and pay for it, because that's just, like, you can't mix it with another 5 to get your free round down. So that's kind of the solution path. You can go ahead and type it real quick. So as always, we're going to need a scanner object. And we're given n and then all the items. So let's just store a total. So we have to print the total cost, including tax. So for each item, so we're going to have to pay for the item. So let's take care of that now. And then we're also going to have to pay the 30% sales tax, rounded down, of course. So that takes care of that. But then we also want to keep track of the number of 2, like the 2 remainders that we have. So we've got 0 remainders, 1 remainders, and 2 remainders. The 1 remainders we don't have to worry about. But in the 0 remainders we also don't have to worry about. We can just check them out as we go. But the 2 remainders we kind of want to save for later if we can. So boolean free 2 equals false. Actually, yeah. So if price mod 3 is 2, so if it's 1 with 2 left over, then if we have a free 2, we have to do something. Otherwise, we have to do something else. So if it's a free 2, that means we don't really we don't care about it, but we want to set free 2 equal to false, because we've used up our free 2. So the next one we're going to have to pay that extra cent for, else we have to pay that extra cent in tax. And then once we've done that, for all of the items, we want to print out the total. Does this have to be long? It does, because we have 10 to the 5th items, and each item can cost up to 10 to the 5th things. But clearly it's not going to overflow long, so we're fine there. And this might not be right. Let's see, is it right? I don't know. It doesn't look super wrong. Let's see if it passes samples at least. So this one we should definitely pass. Yeah, we're fine there. For this one, 39. Uh-oh. So here's the problem. If we have a free 2, then we don't want to have a free 2 next time. But if we don't have a free 2, well, then the next one we get is going to be free, because we'll just combine it with this one. Because you can buy the items out of order if you want. So there's our problem. 38. Okay, cool. So so that is tax evasion. Hopefully you enjoyed the problem. And then we'll move on to the hardest problem in the set, not including the bonus problem, which is 2. So last year we had a problem called 1, and that was the obligatory problem concerning the random mathematical properties of an arbitrary number. This year we have a problem just like that, except it's for the number 2. So last year we talked about primes. This year we're talking about antiprimes. So antiprimes, or highly composite numbers, if you're going to look them up, call them highly composite numbers because that's what everybody else calls them. But I think antiprime is a pretty cool name. An antiprime is a number that has more unique factors than any natural number less than it. So 1 has 1 factor just because it's kind of the vacuous case. 2, it has more factors than 1, so it's antiprime. 3 isn't, because it also has 2 factors, and 2, it doesn't have more factors than 2. 4 does have strictly more factors than both 1, 2, and 3, or all 3 of those, and then you can keep going, etc. The next one after 12 is 24, and then 60, I think. So there's that. One thing to notice is that the upper bound for the number of unique factors a number can have is cube root n, and if a number can only have cube root factors, you can only have at a max cube root n different antiprime numbers less than n. So that tells us right away there cannot be that many antiprime numbers. And in fact, although that bound is like 250 or so, 215, really there are only like 48 that we care about. So if we can just figure out those 48, then for all of these input cases, we can really easily just iterate through all of the antiprime numbers and find the first one greater than or equal to the query number. So there are a bunch of ways of doing that. One way, which I can show you, is kind of the cheaty way, but it kind of works as long as you generate them yourself. So last year we learned to check if a number is prime. One trick you can do is only count up to the square root of that number, because if you know one factor less than the square root, then you know the other factor greater than the square root. So what we can do, we're going to need a total here, of course. I equal to 1. So if I is a square root, then we want to add 1 to the total. Otherwise, we want to add 2 to the total. So we can do this by hand for 10, for example. So for 10, 10 is divisible by 1. So we'll go here. It's also divisible by 10, right? Because 1 and then 10 over 1. Then we'll try 2. 2 will work. 10 over 2 will also work. And then 3 doesn't work. So this if statement never gets executed. And then 4 is too big, so we won't check that. For a number like 9, though, it also will give us the correct answer, because it'll give us for 1 and then for 9, and then 2, this if statement isn't true, so that won't happen. But then for 3, since 3 is the square root of 9, or 3 squared is equal to 9, we'll only add 1. We don't want to count 3 twice. And we want to return total. So what we can do is we can make an int array. This is slightly bigger than 10 to the 8th because this is the biggest number you have to worry about. We give that to you in samples. So oops, num factors dot length. So we're going to get the number of factors of each number. This has to be static. And then once we do that, we can store the highest number of factors we've seen so far. So if it's a new record, we're going to want to add it to a list of highly composite numbers. I'm going to do a tree set because that's easier. And that way we can tell if we've done it right so far. So here, this will work. Also, I want to just do this. So I'm doing this on a slightly faster than average computer right now, but it'll give you some reasonable idea of how fast we're going. So this, yeah, so right there we just check the first 10 to the 6 numbers. They're 2 times 10 to the 6. So we can run this right here, and it will tell us this is just kind of a simple brute forcer. If we make this small observation that we only have to go up to the square root of a number, it can really quickly tell us how many factors every number has just kind of by brute forcing it. So I'm kind of stalling here with what I'm saying, but it turns out there's a much better way to count the number of factors if we're doing it for all of the numbers, right? We can, because here we're not just counting the number of factors of one particular number. If that's all we're doing, this way works fine. But here we're counting the number of factors of all of the numbers. So, oh, this is way too big. We have an extra 0 there. But anyway, you get the point. It would, we're basically done. That took, I don't know, maybe a minute, 2 minutes. So you could easily do that in contest and just get all of the things, all of the highly composite numbers. So we'll just do it really quick just to see if it works even. Uh-oh. That looks right. Okay. So here's one problem. Here's another problem. Okay. So 1, 2, 4, 6 up to 10. And if we make this much bigger, there you go. So those look great. Yeah, I bet those are probably right. Those look reasonable. Look like numbers that have a lot of factors. They're all there's math 24. There are a bunch of ways to get to 24. So, all right, so this works. This will take about a minute to do if you do it right, but this is a super cheesy, gross solution that doesn't feel like it should be the right one, and it turns out it's not the right one. So a much better way of doing this that actually passes within the time limit without hard coding things and other grossness is to do this. Also, this what I just showed you doesn't really work in Python because Python is notoriously slow. So to pre-compute all of them in Python, this is what you got to do. So we're going to count the number of factors each number has by a similar method to the prime sieve. I think Euler invented it. Euler. I don't know. I don't know who invented it, but it's similar to the prime sieve. So we're going to count from 1 to factors.length. And for each number, we're going to mark all of the numbers that it is divisible by. or that that are divisible by it. So this is a super important part, j plus equals I instead of j plus equals 1. That makes it a really fast algorithm. N log n in particular. So this will count the number of factors each thing has. So we're going to iterate through all the things that are divisible by 1 and increment them by 1. Then iterate through all the things that are iterate through right here all the things that are divisible by 2, because I is going to be 2. Then iterate through all the things that are divisible by 3, and do that. So if we print out the all the antiprimes, here are all of them up to 10 to the 7th. You'll notice that took like a second, maybe 1 Mississippi. I don't know, something about a second. We could time it, but it doesn't really matter. Clearly less than 5 seconds. So since that works, all we have to do now is iterate through the queries. So we're going to need a scanner. Uh-oh, what did I do? So we're just going to print the ceiling of that number for each of the inputs. And then obviously we don't want to be printing our debug statements here. So let's see if this works. 1, 12, 24, 108. Looks like it works. Okay, cool. So so that is the solution. One thing you might be kind of interested in is like this really looks like it's an n squared for loop, right? It looks like you're going up n things and then you're going up almost n things as well. But it turns out it's not. I said earlier that it's n log n, and you might be wondering why. That's kind of weird. So if we look at it, when I is 1, we iterate through all n things. Then when I is 2, we iterate through n over 2 things. Then when I is 3, we iterate through n over 3, and we keep going like that. Oh, not 1 over 3, n over 3. We keep going like that up until I is n, in which case we iterate through n over n things or just one thing. And that's the same as if we just factor out an n. Same as this. And this, if you'll notice, looks a lot like the harmonic series. So because it looks a lot like the harmonic series, there are a bunch of calculus tricks you can do. And since it's the harmonic series, this can take the integral of this, and it's smaller than the integral of 1 over n, or the integral of what, log n. So, or the integral of 1 over n, which is log n. And that's why that's n log n. And you can prove that mathematically, but nobody here really cares. They just want to know how to do the problem, right? So, so that is problem number 2, or problem 2, which is problem number 6. Hopefully you liked the problem. I know it was really tricky, and it's kind of hard to think this up in contest, but it's really not too hard of a solution to type, and it's a nice thing to know how to do. Like prime sieve is an interesting way, and if you really understand prime sieve, if you've got like a really deep knowledge of it, this is something you could apply it to that's not really related to prime numbers as much, but it's still an interesting concept of the fact that this type of for loop structure works for other things, and that lets it be really fast. Alright, so that was all of the problems in the set. If you were able to solve 5 of them, the competition obviously hasn't happened yet. It's May 12th right now. But if you're able to solve 5 of the problems, then we're planning at least on giving you the bonus problem. So I can open that right now. So the bonus problem is Tic Tacs. So how this game works is you've got some board game, or some board, and Alice and Bob are playing a game on it. Ooh, that's not good. Okay, straight lines. So you've got this board, and initially the board is full of Tic Tacs. So we'll just draw a bunch of. You've got all these Tic Tacs on the board. And you've got the Tic Tacs on the board, and then when it's your turn, what you have to do is you have to take some positive number of Tic Tacs from the board. So I could take like these 4, for example. And they have to all be in the same row, and also they have to follow the following rule. So you can't ever take some Tic Tac if that would leave some Tic Tac above an empty space, or some Tic Tac to the left of an empty space. Okay, the ones on these ones don't count. Obviously, this can be to the left of an empty space. This can be above an empty space. So like I can take these 4, but I can't take these 4 if the top ones haven't been taken, because it would leave these ones like above an empty space, and obviously I can't like take things that aren't all in one column, and I couldn't take these ones because these ones would be to the left of an empty space. So you got to take them from the left, and you got to take them kind of from the top. But then once those 4 have been taken, that opens up these 4, so you can take like these 2 maybe. The next person can take this one, then this one, and then these 2, right? So kind of like that. So you see the pattern. So you have to take Tic Tacs every turn, and the winner is the person who takes the bottom right Tic Tac. So this one right here. And you obviously make choices so that you want to be able to take that last one. So you don't open this one up for them unless like you have to, and if you have to and they can take it, they're just going to take it and win. And then to make the game a little bit more fun, there's this extra rule. So both players have K skips. So K is just some number like 3. Both players might have 3 skips to start with. And the goal is, how do you optimally play, or how do you figure out who's going to win given a full board and the number of skips both players have. Both players have the same amount. So if you haven't seen this problem in contest, I definitely recommend doing it on paper and trying to figure it out, because it's a pretty interesting problem, and it's tricky, but the solution's pretty cool once you figure it out. Like it's an interesting solution. It's not super hard to implement or anything. Like kind of the other problems have been pretty quick, just like 10 lines or so. This one's the same way, but figuring out how it works is pretty cool. So pause the video, try and do that. And since you're going to keep watching, I'm assuming that you've either tried or given up, or figured it out and want to see if you're right. So I'm going to go over it here. So the first thing to notice is that skips don't matter at all. And why is that? Well, let's say you and I are playing a game, and if neither of us have any skips, the board's in a position where if I play optimally, I can force myself to win every time. Well, if that's the case, I just won't use any of my skips, right? And then if you use one of your skips, well then, now you're in a winning position. So if neither of us had any skips, you would win. So since you're in a winning position, and I have one more skip than you, I'm going to use that skip when it's my turn, because then I'd be in a losing position, to make you in that losing position. So every time you'll use a skip, I'll just counter the skip with my own, right? So, I mean, it'd be stupid for me to use a skip if you haven't, and then if you do use a skip, I can just block it with my own. So, like, skips don't even matter. There's kind of a red herring. So once you know that, the question is just, for a given board, assuming nobody uses any skips, who's going to win? And let's start with a board that's like 4x4, for example. Oh, I want a full. Okay, there we go. Just ignore the blue lines here. So here's our board, 4x4. You can red brute force and check this, but I'll just kind of give you the optimal strategy. So let's say I do this. What we're going to make our invariant, which is like just something that is always true, is these 2 rows right here are going to be the only rows that I take Tic Tacs from. right? So you're going to take all the Tic Tacs from these rows, the rows 1 and row 3. I'm going to only take rows from row 2 and row 4. And since that's true, you're obviously going to take this row, because we're going to run out of Tic Tacs eventually, and you're going to take the bottom row, so you're going to be the one who wins. So if I take these 3, you can prevent me from having any moves on your rows by taking the 3 beneath those, right? And now I'm forced again to only take this one or this one, this row. So I've got these 3 open to me and this one open to me. I don't have any of yours open to me. So if I take these 2, you can again copy the row beneath me, just do the same thing. And then we're left in this situation, and then maybe I do this again, then your optimum move is to do that, and maybe I do that, your optimum move is to do that, and then I only have that move, and then you win. So obviously, it turns out there are a lot of other ways you can perform winning moves other than just copying beneath me. So if you find some cool, interesting way to force a win, feel free to leave in the comments or send me an email or whatever. But this is probably the easiest one to figure out. So you just copy the row beneath you. So that solves it for an even numbered thing. If it's even by even, Bob wins. In fact, the width doesn't even really matter, right? Because none of the assumptions I made were dependent on the width. If it was 3 wide, you could still copy the row beneath you always. So like the width doesn't really matter in the case that it's an even height. But what about the case where it's an odd height? Well, I know that if it's some even height, then the first person to go is in a, like, if I can get it to some even height, then the first person to go is going to lose, because the second person can just copy all the moves they make. So if it's an odd height, if I go first, I'll just take the first row. And now it's the same as it being an even height, but you going first. So since it's an even height now and you're going first, I know I'm going to win. So this is just simplified to the same problem we had before. And now, since before I was at a losing position, now you are, because you're the one who has to go first, even though you go second. You're going first here. So in this situation, if Alice and Bob both play optimally, we just know that Alice is going to win every time, because she's going to take the first row, and then after that, just use the same strategy as before. So since we don't have to actually program what those moves are, this is a super easy problem to code. So we can just print. We're gonna make a new scanner. If the new scanner's next int mod2 is equal to 0, that means it's even. So the second person can just copy all the moves, so Bob wins. Otherwise, Alice is just gonna take the first row and then use Bob's strategy. And since rows are given first, this solution works. So this will just print the answer, and we can run it on samples just to see. Oh. Bob, Alice, Alice. All right, cool. So there you go. There is the solution to tic-tac-toe, or maybe Tic Tacs, I think it's called. Yeah, Tic Tacs. Hope you enjoyed. I thought it was kind of cool that the hardest problem in the set has the smallest solution, just kind of one line of code. Of course, you can make this more pretty by making it multiple lines, but it's kind of fun that the hardest problem is the easiest to code. So I don't know. Hope you liked it. Hope you liked the problems. Hope you had fun. If you didn't like the problems, or there was a mistake, or you'd like to see your code, feel free to send me an email. All of your advisors should have my email. Otherwise, it's 13dharmeyer@gmail.com. Harmeyer is Harmeyer. So yeah, feel free to let me know what you think, and we hope to see you again next year, because it's people who are excited about computer programming and stuff like this that help keep these programs alive. and let us have fun. If you have any comments about these or questions that I didn't explain very well, or you're wondering like why the code works or what you did wrong and you'd like to get your own code, yeah, again, just let me know. So thank you for watching, and goodbye.